Let's try to reassure perhaps the technologists who will be watching us. There is concern, yes, that people might become unnecessary.
But those who think that artificial intelligence and decision support systems will replace humans are deeply mistaken. In this case, a human is irreplaceable.
We ended up in a situation where, at first, there was chemical analysis. The drawback was that it took a long time, while what was needed was speed, efficiency, and less labor. Laboratory setups appeared.
At this point, the technologists, so to speak, really got into it. Technological information can be used not only for studying technological processes and accounting, but also for managing technological processes.
To manage a process, you need to measure it. OSAC provides the data. Accordingly, the automated process control system using this data can already make certain management or controlling decisions regarding the technological process. Colleagues, good afternoon. Today we've gathered for another conversation with Alexander Barkov, whom I've known for many years. He is probably one of the experts with the most extensive experience when it comes to flow systems and express analysis. My name is Arseniy Trushin. I am the CEO and founder of XRF, LLC company. Today we are going to take a comprehensive look at a wide range of various perspectives on the implementation of XRF online analysis for the monitoring of continuous industrial process streams in detail. We are going to discuss this important topic with Alexander Barkov, who is widely considered to be one of the most highly experienced and knowledgeable colleagues working in this field today. Welcome. Please enjoy. We will be glad to hear your questions. Good afternoon to everyone. Alexander, the floor is yours.
Good afternoon, colleagues. Thank you for inviting me, Arseniy, to discuss these topics. I would like to share with colleagues who are just starting out in this field, as well as those who are continuing or only planning to get involved. The topic is interesting, broad, and has a rich history. Well, let's have a conversation. What will be discussed here in this podcast is my personal opinion. I am engaged in project and operational activities in the field of industrial automation. In my previous role, I worked at various manufacturing and production facilities, and nowadays I work remotely, providing support for our group's production enterprises.
Alexander, I always make it a point to ask my guests about their professional background. You mentioned it briefly just a moment ago, but we actually first met, if I am not mistaken, back in 2016, during the time when you were working on site as the head of the automation service. To help our viewers gain a deeper understanding of your experience and expertise, could you please elaborate a bit more on this? Just in a few words, maybe from a broader perspective.
A brief biography. I started as an instrumentation and control mechanic and gradually worked my way up to deputy chief engineer in automation. Later, this position was transformed into the head of the production automation service. I worked for quite a long time as the head of the X-ray spectral laboratory. This is the department that operates the system for on-stream express analysis of beneficiation pulp products in a specialized organization that performs the function of expert support for the group's production facilities and divisions involved in industrial automation. Currently, I serve in the professional role of chief expert within the specialized expert support department.
The topic of on-stream X-ray fluorescence analysis. It has gradually developed over at least a full decade, an extensive period of time. It started with laboratory analysis, with the emergence of the first systems, and then moved on to modern on-stream analysis systems. We are the manufacturers of one of the main components of OSAC, the X-ray fluorescence analyzer, but it also includes a sample collection and delivery system, more comprehensive solutions. And so, as we will discuss today, we will talk in great detail and very concisely about the development of these systems and about the further direction of their evolution. I would like to delve a bit into the history. I think that will also be included. It will be interesting for the viewers to start with the initial prerequisites to see how it all developed, especially since, so to speak, I think you personally witnessed part of this period while working at the enterprise. All of this developed and took shape right before your eyes. That's why I think it will be really interesting for our colleagues to hear, if you could, just a few words about how it all began, and then we'll continue from there. We will continue to develop this idea, what we have now, and what we are striving for in the future.
Yes, let's dive into the history. Because to understand what awaits us in the future, it makes sense to look into the past. Strictly speaking, X-ray fluorescence analysis itself, as a branch of engineering, as an engineering science, engineering systems appeared around 1955. The very first mass-produced analytical instruments began to emerge on the market and were initially utilized within specialized industrial laboratories before they eventually became more widely adopted. In the beginning, there were only centralized laboratories available for this work, but over time, these facilities began to be fully equipped with such equipment. This allowed for the technology to be used directly at the sites where the analysis of mineral processing objects is carried out, where the analysis results themselves are needed, and there gradually began to emerge a widespread need to analyze a very substantial quantity of samples from various geological objects, as well as intermediates, alloys, and a wide variety of industrial materials. The necessary hardware base was created, which in fact made it possible to develop the first devices. These devices were no longer just laboratory setups, but truly industrial ones, suitable for practical application. The main foundation necessary for creating X-ray fluorescence analyzers is naturally the mass-produced X-ray tubes and detectors. The method for isolating characteristic radiation is, accordingly, the growth of crystals. Processing these crystals was necessary to implement the optical scheme for wavelength dispersion. So, essentially, a vast amount of practical experience was gradually accumulated and mass production was finally established. As a direct result of these efforts, we received the very first device around 1955. The rapid development of electronics was also a significant factor, because electronics are absolutely essential to register the signals. At that time, of course, it was nothing like the technology we have now, but it was already sufficient to start solving complex engineering problems. So why did the need for regional fluorescent analysis arise in the first place? Because the predecessor of this type of analysis, which is still very widely utilized and remains the most authoritative, is what we call classical microchemistry. It is an expensive method. It involves the careful handling and management of various solvents and potentially dangerous chemical substances. This specific method is extremely labor-intensive and demanding, material-intensive, and most importantly, it requires a very substantial amount of dedicated time to complete. In other words, it takes a long time. Accordingly, since it takes a long time, the speed of these methods is not what is needed in order to obtain analysis results for the purpose of managing a technological process. That is, the comprehensive data and results provided by macrochemistry and classical chemical analysis methods are perfectly appropriate and suitable for accumulating an informational base for studying technological processes and for planning technological processes in raw material processing, but they are entirely inadequate and insufficient for the operational management of technological processes. It should be noted that during those specific periods, the need for X-ray fluorescence analysis for managing technological processes was, in general, not that significant. The growing demand and requirement for X-ray fluorescence analysis was driven almost entirely by the analysis of geological objects, since there was a critical need for a vast and diverse range of materials for the industry. These are accordingly a wide variety of different metals for producing steels, a range of specific specialized alloys for the radio-electronic industry, and essential electrical equipment and components. And since all of this comes from the earth, naturally the volumes of mineral extraction increased, as did the scale of developing deposits. And accordingly, in order to accomplish all this, it was necessary to analyze a large number of samples. And since chemical analysis methods are time-consuming and expensive, this was a significant and formidable obstacle to expanding the overall volume and scope of comprehensive analytical work, and accordingly to providing the necessary informational support for these processes at the speed and in the volume that was required, because developing any deposit involves thousands and millions of samples. Accordingly, all of this needs to be processed and analyzed, and let's put it in another way, ordinary production workers and field geologists were buried under these samples and the vast volumes that needed to be processed using chemical analysis methods. At that stage of development of industrial mineral processing facilities, low-capacity technological equipment was still being used, which was mainly operated manually. There was some minimal automation, It was already starting to appear, but it was extremely limited. And the entire process, including mineral beneficiation, was, let's say, open and transparent. And the operation of the sophisticated technological equipment that existed at that time did not really require much in the way of any kind of real-time monitoring in the form of on-stream analyzers, because the technological staff developed their own deep observational expertise and intuition, and there were highly skilled and experienced process specialists who could accurately identify and determine the composition of the products just by their color or some other forms of visual perception of beneficiation. Yes, this takes a long time to develop. It's like, machine vision today, except back then it wasn't machine vision, it was human vision that allowed experienced employees to obtain, you could say, analysis results, but based on organoleptic assessment, but the volumes of mineral processing were steadily increasing. And there arose a pressing need for more productive, yet significantly more cost-effective and more efficient technological units, with much higher specific operational efficiency. So industrial technological units became increasingly larger, and these larger technological units were already fully integrated with sophisticated automation systems and tools, without which it became extremely challenging and sometimes simply impossible to effectively operate the complex technological process. So this is, let's say, the first wave. The development and advancement of continuous X-ray fluorescence analysis, the fundamental basis for which, in fact, was the urgent technological necessity to significantly expand the volume of monitoring technological processes and products.
Yes, thank you very much. So back in 1955, was it actually the emergence of laboratory installations, or perhaps the very first continuous analyzers?
Back in 1955, these were complex research lab installations. This period marked the initial beginning of mass production of laboratory equipment for implementing X-ray fluorescence analysis. Continuous analyzers appeared much later, during the decade of the 1970s. You could say that approximately 1975, to give you a more precise but still rough estimate, is when the first continuous analyzers emerged. So, what was this actually fundamentally connected and associated with? This was due to the emerging need for precise analysis. This is primarily due to fundamental changes in technological units and the clear impossibility of further reducing the essential ability for maintaining constant visual control over these complex technological processes. In other words, technological units became larger. How do they differ? They are significantly more productive, far more energy efficient, and require much less physical space for installation. But managing such technological units and monitoring their operation becomes significantly more difficult. As a matter of fact, during the first wave of scaling up these technological units, the specific requirement for flow genofluorescent analysis arose. At that time, electronics had already advanced to a very significant degree, which had previously been the primary limiting factor and bottleneck in improving genofluorescent analyzers. By that time, laboratories for X-ray fluorescence analyzers had already become more advanced, and work had begun on the development of flow analyzers specifically. In other words, flow analyzers did not simply emerge spontaneously on their own because someone wanted to make a flow analyzer, but rather from a fundamental practical necessity. That is, they developed a significant and pressing requirement to increase control over technological equipment and processes. Accordingly, technical means began to appear that implemented this function.
Yes, thank you. So we ended up with this situation. At first there was chemical analysis. Its drawback was that it took a long time. There was a need for speed, efficiency, and less labor. Laboratory installations appeared. Then, transitioning away from laboratory analyzers, again, likely in an effort to reduce analysis time and to make the process faster, we start feeding this analyzer directly, in order to save as much time as possible. Well, at that time, I think samples were supplied centrally. That is, most likely, if we take the courier and burevestnik, it was some room where the analyzer was located, and in automatic mode, probably not a dehydrated sample was supplied, but rather liquid technological pulp products, which allowed even more time to be saved on sample preparation. Accordingly, a certain level of express analysis appears for managing technological processes.
Yes, that is completely and undeniably correct. In fact, it became a distinct and viable possibility. One could certainly say that the comprehensive information richness of process control, which emerged after the initial introduction of the laboratory of genofluorescent analysis, made it possible to create a sophisticated information base that, in its turn, significantly accelerated the overall development of mineral processing technologies, and to control and account for technological products more effectively. And in fact, that's when the technologies really got a taste for it and began to realize that if you could get analysis results even faster compared to chemical analysis methods, then this technological information could be used not only for studying and accounting for technological processes, but also for managing these processes. And a need arose. At the same time, there was a consolidation of technological units. Larger technological units are more efficient, but at the same time, they are also much more complex and demanding to manage. This trend of consolidating technological units had already begun, and it continues to this day. And the more highly efficient the technological units are, the more they require to be equipped with automation systems and higher quality management, the operation of these technological units. And so, by around 1975, the first flow-through genofluorescent analyzers appeared, and they began to appear at a wide range of specialized technological facilities. And this comprehensive and highly detailed technological information gradually began the process of being transmitted to the primary centralized command and control centers of the industrial processing plant. It should be noted that by that time, the first computers had already appeared, not just as experimental installations, but mass production had begun, and the first automation systems emerged. These systems were designed to implement certain local control loops for specific technological process parameters. Previously, industrial automation primarily consisted of a series of local regulators that controlled various individual and distinct technical parameters. At this point, the first centralized data transmission network management systems began to appear, equipped with some early monitors. In other words, this was a preliminary prototype of the SCADA systems that would eventually emerge in the form that we see them today. So it was the complex combination of all these changes. On the one hand, it generated a requirement for continuous X-ray and recipe analysis, but on the other hand, it also laid down the necessary groundwork for their eventual emergence, the spread.
Thank you. I vividly remember how my former colleagues from Kola MMC used to tell stories, probably way back in the 1980s, about the very first installations, where the mainframes still used physical punch cards that were manually loaded in for the original English source code. In fact, there are colleagues who still remember how all of this happened, what it was like, and how it developed. Yes, thank you very much, Alexander. So, we have a starting point. Let's fix it at 1975 to 1980. That's when we saw the first mainframes appear. As I understand it, this is somewhat similar to how we have machine learning algorithms today. At that time, something similar was happening with the development of mainframes. It served as a significant and powerful catalyst for the development of a wide range of sophisticated automation systems. I would really like to take a moment to discuss and explore this further in order to examine the specific nuances of that historical period in much greater detail.
Well, calling them machine learning systems is, of course, a bit of an exaggeration. No, it was still a very long way from true machine intelligence. But indeed, the first large computers appeared, which finally made it possible to process large amounts of information and implement various control functions. Control and management functions, including over technological processes. In other words, if we compare it to today, these would be industrial controllers, PLCs, controllers, but at that time they were based on completely different hardware. With other programming languages, everything is actually considerably more complicated. Still, at that time, the development and implementation of automation systems successfully fulfilled its intended function. It was already quite a complex process. Each control system was highly individualized and required a substantial amount of manual effort to create because the specialized tools used for their development, it was actually quite limited and very poorly standardized back then, primarily because only at that specific time did such specialized tools begin to appear and slowly spread. Programming languages and early computers, of course, were still far from ideal compared to what we have today, but nevertheless they already made it possible to perform these essential functions. It should be noted that it is absolutely impossible to implement flow region fluorescence analysis using any kind of simple local controllers. In this case, it really is necessary to use at least some fairly simple computers, because in one form or another, the complexity of the data requires it. Those flow-through express analysis systems were the first to appear. You could say this was a kind of primitive robotization, and without control functions based on computers, it would simply be impossible to implement such systems.
Yes, thank you. I probably meant that right now we are experiencing an artificial intelligence boom. So, probably, if we look back at that period by analogy with today, there was a boom in the use of computers in industry. There was an attempt to extract the maximum benefit from them, and that accordingly served as a driver for the development of these systems. Yes, quite probably, the automation of various specific processes, such as the delivery of laboratory samples. All right, let's move on. Alexander, so we've set another milestone. So we have a certain period of time when computers first begin to emerge in the field. What happens next after the appearance of computers? We're moving from the decade of the 1990s to the early 2010s, probably covering that entire period.
Yes, this can be called the second wave in the development of continuous X-ray fluorescence analysis. What was it actually associated with? First of all, it continued. There was an enlargement of technological units, increased complexity of technological units, and a growing demand for deeper automation of their operation, automation of monitoring and control, on the one hand. On the other hand, there was an incredibly rapid and transformative development in computer technology, the sophisticated production of advanced integrated circuits, and the widespread proliferation of computing machines, from relatively primitive ones at first to exceptionally powerful and high-performance computing systems. This significant progress made it possible to create rather complex computing complexes and fully integrated and sophisticated automated systems. As a matter of fact, during this specific period, the classic automated process control systems began to emerge, including specialized industrial controllers, practically in the form they exist today, but significantly less powerful and somewhat less sophisticated. Well, essentially, they were not fundamentally or structurally different from what is widely used today. Systems for visualizing technological process parameters, standardization of programming languages, and taking these various changes into account, the labor required to create, operate, and maintain automation systems is substantially and noticeably decreased. That is to say, APCS began to proliferate and spread extensively across the industry, and they became quite powerful indeed. Taking into account the changes in the overall sizes of individual technological units and components, as a general rule, these technological units have been comprehensively updated as a result of a series of specific technical projects for the technical re-equipment of various manufacturing and production facilities, and the need for increased control over technological parameters, including sampling of enrichment products and express analysis of enrichment products. If in the previous period we discussed, it was only the creation of a flow system of express analysis, a significant degree of improvement in the control of technological processes, which may or may not have been present, then the next period, roughly during the period from the 1990s to 2000 to 2010, this stage is already characterized as the creation of a situation where managing technological processes without OSAC systems, at least in the field of polymetallic ore processing, became extremely difficult and indeed nearly impossible. Of course, you could run technological processes, but hitting peak performance without such systems was extremely difficult. So, during this period, we can say that OSAC systems went from being a nice bonus to becoming a mandatory and essential element. The need for such systems finally became very firmly established.
Yes, thank you. I just remembered an interesting fact. When I entered university, there was already the first computer, probably running on a Pentium, back in 2003 to 2004. And in fact, this moment likely represented a significant turning point, a kind of Rubicon, when prices for personal computers, for those very first computers, reached such a low price point due to the scale of mass production, that regular everyday users also began to purchase them for home use. And probably this was also, I think, another significant driving force. including from the perspective of training personnel who would actually have to operate and maintain these machines and systems, as they became an increasingly common and essential part of our daily lives. This also included the very first foundational programming languages that appeared, which were already being taught in universities at the time. Well, of course, it's only natural that all of this is inevitable. If it reaches ordinary users, then naturally it starts to be extensively and broadly utilized for automation in manufacturing as well, and becomes widespread, probably also due to the significant reduction in overall costs and the massive increase in computing power of these systems' capacities. Thank you. We've really dived in and started from quite afar, taking a comprehensive and incredibly detailed examination of these systems. I hope we won't wear out our viewers' patience too much. But I think it's an essential and important foundation as well to understand what the prerequisites were, exactly how it all first began, in order to grasp the direction of further development, where these systems are heading, and what the next major stage will be in the development of these systems. So we've reached the OSAC system, the automated analytical control system. Next, there should be a transition to the automated process control system. You, as it were, directly witnessed this period yourself. So please share more specific details about this transition. What were the necessary prerequisites? What groundwork had already been laid in this area? And how did this shift happen for us from OSAC to APCS?
We'll go back a little to the previous period. If we talk about the 1950s and 1960s, those years were characterized by the creation of some local systems for monitoring and regulating individual parameters of technological equipment. In other words, there was not even any talk of comprehensive automation systems at that time. The next stage came with the development of computer technology and the emergence of large computers. And the development of MOSAC, this is around 1975 to 1980, marks the creation of the first integrated APCS systems, the emergence of the ability to process large volumes of data, the need for increased information richness, and the control and management of technological processes. Then comes the period from the 1990s to 2010. This is a time of rapid development of APCS and the widespread adoption of APCS complexes, as well as the creation of a broad set of tools for their development. The quality of APCS performance increased significantly, as did the quality of the hardware base used to build them. In other words, they became an indispensable and most important element of industrial enterprises. Without them, the operation of production facilities would already be impossible. At the same time, the computing power of such APCS systems became so large. This made it possible to create the first systems for improving the management of technical processes, as well as DSS, decision support systems, and expert systems. During that particular period in history, there were not yet any readily available or user-friendly tools for creating such systems. Here, by tools, we mean highly specialized and dedicated software packages. Widespread development in this area only began to emerge significantly much later on, and for the most part, these developments represented a fundamental shift in the industry. This process essentially involves algorithmizing the work of the best operator, implementing a series of certain sequential actions for the effective management of technological processes and equipment. And this also marked the beginning of the first efforts in creating machine learning systems.
You know, there's actually another very important point here. I'd really like to hear your opinion so that it's perfectly clear for the viewers exactly what the difference is between the OSAGO system and the ASUTP system.
OSAC systems are information and measurement systems. Yes, it's not just some measuring instruments, but essentially a complex of miniature technological equipment that ensures the sampling of technological products from the process, their transportation to the place of analysis, preparation, delivery for analysis, and in fact, the analysis itself. In other words, ASAC systems, they do not. While managing the technological processing, they generate the information necessary for monitoring and controlling technological processes. The task of the APCS system is completely different. They are specifically designed and intended for the management and control of technological units, production technological units, rather than just auxiliary systems like OSAC. And accordingly, they solve different tasks. These are accordingly equipment monitoring and interlocks, implementation of various protections, implementation of monitoring and control of individual technological parameters, and implementation of complex algorithms for controlling the technological processes of equipment. initial startup sequences, complete shutdown sequences, preparations for startup, routine maintenance after shutdown, and preparation for subsequent startups. And accordingly, the capabilities of comprehensive control over individual technological operations and even entire industrial processes. So essentially, that's the difference. To put it simply, ASAC is about the monitoring process, while APCS is about the actual control functions.
To control a process, you need to measure it. ASAC provides the data, and accordingly, APCS, using this data, can already make certain management decisions that influence the technological process.
Yes, of course, one very important factor during the period from the 1990s through to 2010 was that the rapid development of computing technology and automated process control systems made it entirely possible to create highly detailed and comprehensive technological reporting documentation. This was largely due to the complete automation of this entire process. Previously, the introduction of various types of technical documentation for monitoring and controlling technical processes, often referred to as reports, was generally performed manually. During this period, however, the automation of generating these documents was already spreading actively, as well as the automation of calculating complex technological parameters and accredited technological parameters that characterize the quality of operation of technological facilities. This comprehensive standard applies to the enrichment, the detailed processing, and the secure shipment of various technological products, as well as the overall quality of those technological products, the extraction processes, and the strategic use of diverse technological materials. In other words, this is essentially a system of management documentation, which at that time was still in development. As a rule used by people to make decisions regarding the control and management of technological processes, but the entirely complex procedure of generating this information itself was already fully automated and streamlined. And in fact, the formation of this information was, among other things, a fundamental and essential prerequisite for creating a comprehensive information base. To begin the development work on creating decision support systems and software systems for the optimization and management of technological processes.
Thank you. I just remembered another point, the digital twin of an enterprise. It probably appeared a bit later than this period, right? We can also come back to that. Or just a brief remark, what is your opinion on the effectiveness of digital twins in enterprises?
Tasks related to modeling technological processes have existed for quite a long time. In fact, the tools for calculations and modeling of technological processes that have not been implemented on certain technological units. And let's say based on the physical principles and chemistry of technological processes, such tools began to emerge during this period due to the fact that the widespread development of information technology, programming languages, and computing power created unprecedented new opportunities and possibilities. That is, the emergence of a large number of calculation programs in which certain parameters of the raw material composition, approaches to their processing and processing schemes were specified. Accordingly, this made it possible to systematically and automatically calculate the parameters, as well as the expected result parameters, of complex mineral processing operations. At that time, digital twins of production facilities, real industrial enterprises, were not yet being developed because such capabilities simply did not exist yet. But by the end of this period, around the time frame of the year 2010, the initial pioneering research and development projects within this field had already begun, and we encountered the significant and substantial financial costs of training new, highly skilled specialists. In process control, these are the control panel operators, due to the high complexity of managing technological units and processes and the increase errors in the management of different technological units and processes. What is this related to? This is because modern technological units are becoming increasingly larger, and the cost of errors in managing technological units is steadily increasing. It keeps continuously rising, and the requirements for the specialized skill levels in controlling and managing technological units and processes are also increasing. That is precisely why there emerged a significant and pressing necessity for such tools. Consequently, various specialized software and hardware technological solutions appeared, with which it finally became possible to implement these complex systems. However, such systems were not yet extensively adopted or universally implemented at that time, although active development in this specific area was already well underway.
We have finally reached the main and most interesting point, probably starting from 2010 right up until the present day. Once I was at a very specific facility during one of our implementations, talking with some colleagues who also work with X-ray fluorescence analyzers, specifically the flow type ones. These were of the second generation. And I recently heard a very interesting opinion. Basically, the human operator sitting there at the complex control panel started out with just one monitor. Then there were 2, then 3, and sometimes even 5 or more screens. And today, there is such a massive amount of complex information that a person can no longer easily connect all these different numbers together and operate with them effectively in a high-pressure environment. So, in your opinion, how can we? Well, obviously, there are probably various ways and potential solutions, and we all know about them very well by now. Could you please describe this specific situation in more detail and explain how it is currently being effectively addressed?
Well, here probably just a little bit. We will have to delve into the specifics of managing technological processes, as well as the features of the technological processes themselves and the development of the equipment that supports these technological processes. The thing is, what we've been talking about so far, we constantly observe. The process of scaling up technological equipment and the increase in productivity of individual technological units, which significantly boosts production efficiency, but at the same time inevitably complicates the management of these individual technological units. This, so to speak, is the primary overarching theme. It runs through the comprehensive and intricate life cycle of technological development and the profound consequences of this change on all the various systems that support the operation of this equipment, as well as the technological processes implemented on them. The phenomenon you mentioned is significant, that indeed those complex automated process control systems, commonly known as APCS, that these systems are widely used at many industrial enterprises, serving as a fundamental component. They represent a set of local control loops that are responsible for the monitoring and regulation of individual technological parameters and visualization of various operational parameters. And the technological schemes themselves are displayed in the form of detailed mimic diagrams on the screens of individual operator workstations, control panels, and centralized control rooms. This is traditionally what an SDP represents. As a rule, in addition to the various screens displaying complex technological schemes and mimic diagrams, there are screens that show detailed numerical data and statistical information in graphical form. Furthermore, there are also specialized screens that display aggregated technological information in tabular form. And in fact, a person is compelled and required to constantly, carefully observe and monitor huge volumes of information and subsequently find a way to make critical decisions regarding the management of technological processes. That is, essentially, a person is entrusted with the responsibility of a rather complex, in fact, an almost impossible task of controlling and managing highly intricate and sophisticated industrial facilities. But that's not the whole problem. The problem is that another thing is that technological processes incorporate specialized technological equipment, and consequently, the processes of controlling them necessarily involve inherent factors, such as delay and inertia. What does this lead to? Consequently, this results in the influence on the technological process, which is made by changing certain set points of a technological parameter may not have an effect here and now, but only in the distant future. This presents itself in a variety of distinct ways for different types of modern technological devices. These specific time lags and inherent inertia vary across systems, but nevertheless, this effect is absolutely critical. And unfortunately, or perhaps fortunately, that is just the way it is by its very nature. These specific time intervals associated with operational inertia and the necessary reserves within various technological processes, along with their associated parameters and critical metrics, do not correspond in any meaningful way to the standard duration of the daily work shifts assigned to the technological personnel on site. To put it another way, if the duration of a control room operator's work shift is subject to change or variation, for typical facilities that do not use a rotational work schedule, it is generally established that, as a rule, the shift lasts for a full 8-hour period. If it is a rotational work schedule, then as a rule it is 12 hours. However, the inherent delay and inertia in changing technological parameters as a result of direct interventions performed on technological facilities can be accurately measured in terms of hours, or even entire work shifts. Sometimes it can take days, even weeks. Therefore, it is difficult for a person to make decisions regarding the management of technological processes, including it is difficult. That is, on the one hand, we have huge amounts of information that a person must at least simply perceive, on the one hand. On the other hand, it is necessary to understand that the results of interventions on technological equipment and processes do not manifest themselves only immediately, and not always right now, but sometimes only after a considerable amount of time. What kind of particular phenomenon is still persisting right now? The consolidation of technological equipment continues. If we look at traditional beneficiation plants, which still exist but are becoming less and less common, the advanced modern beneficiation plants that are currently being built, they sort of, as a general rule, they are constructed using, let's say, technological equipment specifically represented as a single unit for carrying out a single technological operation. But when we consider the context of exceptionally massive and large-scale industrial equipment, if we take a moment to look back at the specialized grinding sections found within modern beneficiation plants, they typically consisted of a large bay where, as a general rule, there were a vast array of dozens of individual grinding mills, each one supporting a certain number of similar technological grinding schemes for the processing of raw materials or various intermediate products. Now, if you were to visit a beneficiation plant that is currently being meticulously designed, actively built, or, as is often the case for the most part, already fully in operation today, what does the grinding section currently look like today? It is comprised of a total of 12 exceptionally powerful and advanced technological units that handle the grinding of all the ore that is delivered directly into the beneficiation plant. Because there is such an extreme concentration of production capacity in only a few technological units, this makes the overall cost of management errors, which is the price of a mistake, extremely high for the organization. And that's on the one hand. On the other hand, even a seemingly minor improvement in the efficiency of managing such a technological unit can have a significant impact. It can yield a very substantial economic effect.
I'd like to briefly summarize now so that our viewers can clearly understand everything. We've just finished discussing the third wave, which involved the process control systems and the consolidation of processes. Indeed, massive industrial units are present at all contemporary industrial enterprises. And now, let's transition our focus over to the fourth wave. This is already our much talked about machine learning algorithms, artificial intelligence, and various other related technologies. What are the current tendencies and trends in the application of machine learning algorithms? Where will it actually be integrated? For what purpose? With what goal and what effect? Significant or insignificant in your opinion? Can it have for manufacturing enterprises?
Yes, indeed, in this day and age, decision support systems, DSS, are becoming increasingly widespread and prevalent, as well as advisory systems and various other systems for improving the overall management of technological processes. And what, one might ask, has this development in fact led to? First of all, this trend actually took shape during the previous wave, the historical development and evolution of process control systems. At that time, the need for such control systems was not nearly as significant or pronounced as it is now. That is, as I already mentioned, contemporary mineral beneficiation facilities are there is a high concentration of production capacity in individual logical units, and the cost of errors in managing these technical units is extremely high. Additionally, it should be noted that controlling these sophisticated units based solely on visual parameters is highly restricted and significantly limited in scope. Advanced machine vision systems and simple video surveillance are currently used to assist human operators in managing these complex technical units. But the sheer complexity of managing such intricate technological objects is so high, and the potential consequences and financial cost of any operational errors is so great, that entrusting the autonomous management of such equipment and such critical technological units is considered to be an incredibly complex and problematic challenge for modern industry. On top of all this, there is another important factor. It's a social phenomenon occurring in our society, a socio-economic phenomenon. Accordingly, the paradigm of society has changed. There has been, and continues to be to a significant extent, a liberalization of people's consciousness. And accordingly, people no longer want or intend to spend their entire lives working at a single manufacturing enterprise. They are becoming more mobile. In addition to those challenges, there is also the gradual exhaustion and depletion of the mineral resources that were previously exploited, and the rotational work system is becoming increasingly commonplace across the industry. This rotational work system further increases the overall mobility of the workforce. As a result, there is a steadily increasing requirement to separate employee competencies. That is, to separate these specific competencies from their holders. In other words, the accumulated knowledge and skills in process control and management, as well as knowledge about the technological process itself. These need to be somehow crystallized into certain tools and systems that would allow maintaining the quality of process control and management when personnel changes occur. There is an increasing need to accelerate the training of technological personnel because there is a high turnover of technological staff on the one hand, and accordingly, new people are coming in, and there is no opportunity to wait a long time until they master the specifics of process control for a particular technological object. It is necessary to ensure that this happens in a relatively short period of time. A person should be able to master the tasks of controlling and managing this technological object and successfully maintain and operate it. So essentially, all these phenomena, they establish the fundamental prerequisites for the overall economic efficiency of the initial creation and the subsequent daily operation of the complete system. A machine learning system, a decision support system, and a system for improving the management of technological processes. To understand the difference, that is the DSS, decision support system. These are semi-automatic systems that suggest how to manage technological processes, but do not control them directly. Automated control systems for technological processes are systems that fully control the technological object. The costs of creating such systems are exceptionally high and substantial. This is because they are formed from the significant labor intensity and specialized human resources invested in them. In other words, creating such systems requires a substantial amount of labor from highly qualified and experienced personnel. And because of this, creating such systems is quite expensive, a costly undertaking. But since the cost of errors in monitoring and controlling technological processes and units is increasing due to their concentration, it is becoming economically viable. Moreover, the software applications and tools for creating such systems have become increasingly widespread and readily accessible. All this has led to the fact that today we live in a world where creating such systems is not just a wish or an optional feature you can choose to have or not have. It is a matter of ensuring the economic efficiency of production and even a question of the possible survival of the enterprise. Because the world is different, people are different, machines are different, everything is different, and accordingly, everything needs to be managed differently. This particular scientific phenomenon is gaining significant momentum and speed, as one might commonly say.
Yes, that's absolutely great. I want to take a moment to reassure perhaps the dedicated technologists who will be watching us today that this innovative system is much more likely to assist and support them rather than to simply replace them. Because right now, as we can all see, our news sources are constantly and completely filled with this kind of overwhelming information. For some people, this causes a significant amount of concern, making them worry that they will eventually become completely unnecessary. But for now, at this current stage of technological advancement, these systems are still more like helpful assistants. In the process of decision-making, it is a tool for a person that can be exceptionally beneficial and highly advantageous, so to speak, to help process large amounts of data and increase work efficiency. On the one hand, we are currently experiencing an artificial intelligence boom with machine learning algorithms. On the other hand, ever since the advent of personal computers, a significant amount of data has been accumulated in digital form. This is quite a large array of data and information, big data, which can also be analyzed and explored. All of this creates the prerequisites for more efficient and probably more automated management of technological processes. But at the same time, there is a widely held opinion that, but quite probably, just like back in the early 2000s, there was a massive boom in websites which led to a well-known scenario. It burst when the dot-com bubble finally popped and when all the investments suddenly collapsed. There is always a significant risk of overestimating a powerful tool that has only just emerged on the market, such as artificial intelligence. Looking at it from this specific perspective, On the one hand, we must continuously keep our finger on the pulse of innovation and make sure we don't fall behind the rapid pace of the technological process. On the other hand, we still need to keep a cool head, stay rational, and truly understand where the euphoria should end, and quite probably not get carried away with thoughts that our factory will be run by artificial intelligence and human workers will eventually become unnecessary. What is your attitude in the current situation?
Thank you for the question. These are very timely issues. Those who think that artificial intelligence, decision support systems, and replacing humans are the same thing are deeply mistaken. In this case, a human is irreplaceable. Let me explain why. The fact is that all these systems, whose creation is quite expensive, are designed to monitor and control technological processes of equipment during prolonged steady-state operating modes. That is, they are not fundamentally intended for, nor are they trained on datasets from startup operations, or from shutdowns of technological units, or from any transitional modes. In this specific context, a human is absolutely irreplaceable and essential. Moreover, a human remains indispensable not only because creating such complex systems is an incredibly difficult undertaking, but also because there are strict industrial safety standards and legal frameworks that must be followed. And the startup or shutdown of such technological units, or changes to some key parameters of their operation, these actions always carry substantial and significant risks. There is always the possibility that something can go wrong. And here, it is absolutely necessary to have a person who is ready at any moment to take control and make the necessary decisions to provide the required intervention. Here it's just like, fundamentally speaking, those sophisticated autopilots that assist pilots in navigating airplanes, but no one is planning to phase out or replace the pilots just yet. And it should be noted that piloting an airplane is such a widespread task because there are a vast number of planes in operation, and the tasks of takeoff and landing are the very same type of transitional mode as in the complex management of technological processes, starting up and shutting down technological units. Nevertheless, it always poses a significant and serious danger, and that is precisely why human involvement is necessary, even if he is not directly performing any obvious actions. But in such critical situations, he remains completely focused on the task at hand. And he always understands that there is a possibility that something unexpected could go wrong. Consequently, he may be required to make the necessary decisions to intervene with the equipment.
This probably reminds us of the same tool as the personal computer, which entered our lives back in the decade of the 1990s. We probably collaborate closely in tandem, right? And again, as I understand it, there are certain risks. What if the system ends up behaving like that? But, as they say, even a stick shoots once a year, something could fall, there was no backup and so on, and then the array is lost. So who at the enterprise would be responsible for starting things up manually and so on? In other words, what is the alternative path if this system fails? Well, it was irretrievably lost, so that's also probably a certain risk as well. To rely entirely on the information system operating automatically.
Yes. Here we should probably also mention the specifics of the technological equipment in operation. That is, you see, any sophisticated pieces of technological equipment undergo significant changes in their core technological parameters during operation, due to the gradual accumulation of various types of wear and tear over time. This occurs during the periods between repairs and accordingly results in changes in its parameters after comprehensive maintenance and repair operations. This is also related to the fact that this factor has a very strong impact on the complexity of creating a decision support system and a system for improving proper technical processes. In other words, the equipment we operated today is not the same equipment we operated yesterday. It is constantly changing. Its parameters are constantly changing. Yes, this process occurs at different speeds, but it needs to be taken into account. This factor is not immediately apparent or obvious to many people, but it actually has a very profound and significant impact on the overall operation of such systems. By the way, this also has a very strong influence on the gradual process of obsolescence of the system for improving the management of technical processes within these advisory systems. In other words, the effective operation of complex advisory systems and advanced control systems requires a program of constant maintenance, primarily because there are, so to speak, certain adjustable parameters that tend to degrade and drift over time if this system is not properly maintained and cared for, not retrained on newly updated information, and these parameters are not adjusted, it will degrade in a relatively short amount of time and become entirely ineffective and useless. That is, after such degradation, they might even result in more harm than actual benefit. Therefore, operating such systems is not exactly a cheap or simple endeavor either. But nevertheless, it remains highly useful, people continue to do it, and it's important to fully understand this entire process. It's not like you implement the system once and then just live with it. Nowadays, it doesn't work that way.
You know, an interesting thought just came to my mind. There is a very specific reason why we gave that little introduction earlier. Yes, if you look at how all of this actually developed, on the one hand, with the initial appearance of OSAC back in 1975, at first it was probably viewed as just a useful optional feature. But now, quite honestly, I think it is extremely hard to find any modern factory being designed today where such a sophisticated system with integrated process analyzers isn't included right from the very beginning. I think, in all probability, the exact same thing will happen with these new decision-making assistants. At some point in the near future, this will become, or rather, it will be standardized across the industry, and will eventually crystallize into several distinct products from different companies, which will possibly compete with each other. And perhaps in the future, it will also probably become some kind of integral part. Just as the OSAC system has a control trial that monitors the system's operation, in this case too, there will most likely be a type of feedback loop for the decision-making assistant. It seems to me that with a very high degree of probability, this will also probably become a standardized solution when the planning and design of factories takes place in the future, which perhaps will it be standardized and incorporated during the factory design stage?
Well, here I probably don't quite agree with you. Let me explain what makes it specific. The reality of the situation is, as processing technologists often say, unfortunately, a design ore never actually gets delivered to a design beneficiation plant. Design ore, in other words, what we design, what we expect, and what we actually get, in the end are often entirely different from one another. The process of implementing and creating advisory system improvement systems is a very lengthy, intricate, and highly complex undertaking. It requires certain information databases, which serve as the foundation for training these systems. Until the technological object is launched, until it starts operating, it is simply impossible to train the system when there are advanced tools for creating management systems that speed up and reduce the costs of their development. They really do exist. They are already available for use right now. Unfortunately, due to geopolitical changes, the availability of such tools has now steadily decreased. But there are significant local domestic developments currently being carried out, and overall they are not at all inferior to their foreign counterparts. The process is ongoing, but it is not yet very widespread, primarily because it remains quite complex, lengthy, and extremely labor-intensive. At this point, it probably makes sense to point out that in order to properly implement a system for improving decision support systems, certain specific conditions are absolutely necessary. You simply can't just go to any facility. You can't just say, now we're going to perform a miracle here and you'll suddenly be happy. It doesn't work that way. These specific types of complex systems require a very solid and well-established foundation. So what does such a foundation actually consist of? It is the essential and fundamental quality of the basic automation work, which effectively means the technological equipment itself as well. Let's start with the first point. The technological equipment must operate reliably, meaning the number of failures and stoppages should be minimal. The duration of long, stable operation of the equipment, the periods of steady state modes should be as high as possible. The number of transitions should be minimal. In other words, everything should already be quite good and stable. That covers the very first point of our discussion. Second, all of the fundamental automation systems, including all local control and management loops that are absolutely essential to ensure the continuous operation of the equipment, must provide the required control and regulation parameters. This is the second basic condition. The third condition is the comprehensive level of informational richness and detail necessary for monitoring and managing these complex technological processes. In other words, we must ensure the monitoring of such parameters and the acquisition of such technological information as is necessary to enable the automation of technological process management. At each technological facility, these are highly specific and unique conditions. They are carefully identified and documented as a result of carrying out comprehensive surveys and audits of technological sites. That is, when implementing advisor systems or advanced control systems, what is the actual starting point for the process? A specialized team of experts arrives. They analyze the technological facility, carefully observe how the system operates, whether the conditions for stable operation of the technological equipment are met, and whether the requirements for basic automation are completely fulfilled. A whole range of issues is raised from
letters, and sorry to interrupt, but for example, the percentage of downtime, the percentage of failures, these are just reference points for the viewers. So,
well, let us look at the situation in this specific way. Failures should be episodic in nature. They certainly shouldn't be systematic. In other words, there shouldn't be disruptive stoppages occurring during every work shift. And so, a stoppage of key equipment, this should be, let's say, a fairly rare and exceptional occurrence.
Once a month, once a year?
Well, it could be, let's say, no more than once a week, roughly speaking, at least. The less often, the better, so that it's once a month or perhaps even once a year. In the modern world we live in today, that's probably not very realistic, because modern technological units, as a general rule, demand consistent and frequent technical maintenance, meaning, for example, twice a month or at least once a month. They are regularly stopped for this maintenance, during which any components showing signs of wear are carefully replaced and thorough inspections and checks are carried out. But this is a regular routine procedure that absolutely needs to be performed, among other important reasons, so that these unscheduled shutdowns and malfunctions don't occur. That's regarding the stability of the equipment's operation. As for guaranteeing the comprehensive quality of regulation, as well as the essential fundamental mechanisms of the system controllers, for example, if we take typical cases, let's say for flotation, this includes monitoring and regulating the level in flotation machine chambers or the supply of compressed air to the flotation machine chambers. A strictly acceptable control error must be guaranteed at all times. Control loops should not enter into any self-oscillating processes or become completely unstable. That is, when designing systems, certain regulation quality parameters are carefully established and defined. And as a matter of fact, the primary objective of manufacturing technological equipment is to guarantee that technological processes within this equipment proceed correctly. It is fully outfitted and equipped with all the absolutely essential automation tools, and it requires that certain specific accuracy characteristics of regulation are guaranteed and strictly maintained. Here is another, probably the third and most expensive element, which is absolutely necessary, and without which the entire creation process becomes completely impossible. The successful implementation of creating ACS and APCS depends on the lack of control over specific technological parameters, which in fact provide the necessary foundation to create detailed informational models of the technological process, on the basis of which, in fact, automatic control is effectively carried out. That is, these are the algorithms for improving control that are implemented. In order to effectively manage and control several critical operational parameters, you need to closely monitor and track them on a regular basis. Well, as a general rule here, that is, if we take, for example, mineral processing and beneficiation production facilities, then, as a rule, these are material flow instruments. Specifically, these are specialized weighing scales and high-precision flow meters for measuring density. Various techniques and methods for accurately measuring the movement of material flows, accounting for and dosing reagents, and in general, consistently ensuring high-quality dosing of agents. Why is this so important? Because it is the most powerful influence on the flotation process. There is nothing stronger. That is, its impact on the chemistry of the process is the most significant for the technology. If it operates unstably, if there are any problems, then talking about any optimization measures is pointless. And essentially, we need to accurately calculate the recovery rates, we need to precisely determine the overall yields, and this can only be effectively achieved without the need for sampling and express analysis of beneficiation products. The information richness of control and management systems must provide the ability to assess at any given moment the key parameters of equipment, operation, and technological processes. And to do this, they need to be monitored. As a rule, this refers to beneficiation and aggregated technological parameters. Aggregated technological parameters have the particularity that they are not measured directly. It is impossible to measure them, they are calculated. They are calculated from a large amount of information. This information needs to be available. If we do not have this information, we will not be able to calculate, we will not be able to monitor, we will not be able to assess whether we are working better now or worse. If we cannot assess, then how can we manage this process? In other words, it simply becomes impossible. Therefore, the growing and essential requirement to expand the depth of informational richness control, and management of technological processes, functions as a significant structural barrier that prevents enabling the creation of a highly sophisticated and advanced management system. So there are these three pillars, as I already mentioned: equipment operation stability, the required quality of basic automation, and the necessary informational richness. To put it another way, if any of these specific conditions are not properly satisfied, then implementing an advanced management system or a decision support system becomes either completely impossible or entirely ineffective. Yes, in the modern world, let's put it this way, there are plenty of charlatans out there who might come and say, "We'll do everything for you, you'll be happy, just pay us the money, we'll research something for you." But in the end, they do nothing. Everyone's had that experience.
One of the primary objectives of our podcast is precisely to proactively communicate these kinds of fundamental concepts to our colleagues and team members. Thank you for sharing these concepts and helping us avoid stepping on the same rake. So when someone comes along and makes a promise to automate every single part of the process, despite the fact that there are frequent daily stoppages, low information density, or a lack of basic automation, I hope our colleagues will find this useful to listen to, draw certain conclusions, and relate it to themselves, including to their current workplace and the enterprise where they are now employed. So, actually, thank you for sharing in response to my clarifying question. Sorry for interrupting. I think it's important in order to provide the maximum benefit to our viewers. It is helpful that you brought up the subject of information density, since this topic is closely related to the work we do. Regarding the implementation of continuous online X-ray analysis systems, I would like to clarify an important question. What are the primary key reference points or critical boundaries in terms of information density? In other words, what specific requirements should be ensured from the perspective of continuous online analysis systems?
There are several factors that need to be taken into account here. Rapid express analysis systems offer comprehensive and detailed analysis of various specific technological products and intermediates at a specific frequency and with a certain level of accuracy. This includes the range of sampled and analyzed products, the frequency at which analysis results are delivered, and the metrological characteristics. The comprehensive results of the analytical data, in fact, are the fundamental parameters by which one can evaluate and determine how well the technological processes and the complex process of managing the technology are provided with the essential and highly detailed information in terms of the overall system of analytical control and monitoring. To begin our discussion, let us first examine the first point, the massive volumes of various technological products that are currently being monitored. For intermediate products, extensive sampling and detailed express analysis are required in such large volumes that at any given moment it is possible to accurately calculate and monitor all key technological indicators. We implement automation for technological operations and processes if we need to be able to calculate the technological scheme at any specific point in time. This is an essential requirement. In some cases, there may be allowances made for certain products, where in some places it is completely and utterly impossible to monitor or sample them because, quite simply, there is absolutely no feasible way whatsoever to take a sample. There is simply no specialized technical equipment or means available for this. In such cases, exceptions can be made. Ideally, we should be able to calculate the technical scheme at any given moment in time. This applies to methods for calculating technological schemes. The indicators of the composition of beneficiation products are of key importance. If we look at the formulas for calculating yields from processing, all these parameters can in fact be calculated without the mass of the flows, based solely on the results of express analysis of the beneficiation products. That is, there is a way to calculate using only qualitative indicators, and there is a way to calculate using both qualitative and quantitative parameters. The more accurately and comprehensively we can perform the scheme calculation, the more effective it will be. This directly relates to the scope of control, as well as the purity of control, the frequency, and the timely delivery of analysis results to Luna. It should be roughly equivalent to the duration of technological process operations, or better yet, be considerably more brief, significantly shorter than the duration of these technological operations. For example, in flotation enrichment methods, the duration of logical operations is considered. It is typically measured in a span of several minutes, usually approximately 5, 10, or 15 minutes. Here are some individual operations, preliminary operations before the main ones, that can last for dozens of minutes, 30 to 40, or in rare cases, even 1 to 2 hours. But it's important to understand that even during these 1 to 2 hours, the operation proceeds unevenly within the technological units. That is, as a rule, the intensity of technological processes within the unit is not uniform. As a rule, flotation is a chain of units. That is, in the very first head units, the operation proceeds with the highest possible intensity. Accordingly, in the subsequent ones, it is less intense. That is why this discreteness in the delivery of analysis results, which has existed since 1975, since the time of its creation, persists. The specific interval of approximately 10 to 20 minutes is not chosen at random or without careful consideration. That is to say, it is grounded quite specifically and precisely upon the actual duration of technological operations, ONA, as well as the rate of change in the overall composition of technological products and intermediates. As for the metrological characteristics of the express analysis results, they are determined by a wide variety of different influencing factors. The first is ensuring representative sampling. In other words, we can measure an improperly or unrepresentatively taken sample with great precision, but who needs such an analysis? That is, we have very precisely measured something that doesn't actually exist in nature. This is the first factor. That is, it is necessary to ensure the representativeness of sampling and the preservation of sample representativeness at all stages of its transportation, preparation, and delivery for analysis, as well as during the analysis itself, so that significant distortions of the composition of the analyzed products do not occur. This is the first factor. The second important factor to consider is that the analysis systems themselves must provide a level of accuracy that is considered acceptable. Regarding the results of express analysis, in other words, there is a standardized reference analytical method based on the results of which the calibration of the process analyzer is performed, and accordingly the error in the analysis results should not be substantially or significantly greater than the results obtained from the reference method. It will in any case be higher because miracles do not happen. Any additional measurement based on the results of some other measurement will definitely provide less accuracy than the result of the primary measurement. That is, in any case, there is always an accumulation of variance and error. Well, I think I have answered the question here.
Thank you very much for the detailed overview of the development of the OSAC SOTP systems. Many thanks to all of our viewers for joining us today. In the very next episode of our podcast, I would like to propose that we take a much closer look at a specific element of this system, namely what our organization does with these specialized energy dispersive X-ray fluorescence analyzers. We look forward to seeing you then. I would like to thank you very much for sharing such valuable information with us today. Thank you to our viewers for watching until the end. A few final words, Alexander, to wrap up the podcast and draw a final line.
First of all, thank you for inviting me. It was very interesting and engaging to have this conversation. I hope that what we discussed was useful and interesting for the viewers. Perhaps there will be some questions from their side, and we can answer them. The long and complex history of the development of regions of recent analysis, including flow analysis, is remarkably extensive and detailed and consequently very interesting. In my career, I have had the opportunity to interact with those people who were actually at the origins of all this, even to this day. Some of these people are still alive and well. Fortunately, thank you.
On PACE, it's a big topic, so dear viewers, we will be glad to receive your additional questions, perhaps including if there are any topics that interest you. And if there's something we haven't covered, please write in the comments and we will definitely take it into account in future meetings. I would really like to say thank you very much.
Thank you.